Hi everyone, this is a brief overview of my upcoming talk at the SCG annual meeting titled Anisotropic Eikonal Solution Using Physics-Informed Neural Networks. So eikonal solution is used for many applications such as travel time tomography and microseismic source localization, to name a few. And we need to incorporate anisotropy to compute accurate travel time since the nature of the Earth is anisotropic. To illustrate the idea, I'm going to use the 2D VTI eikonal equation. However, the approach can be used for TTI, orthorhombic, or even more complicated eikonal equations. Now, the challenge in solving anisotropic eikonal equations comes from the fact that we need to have solve for these terms like this one multiplied by this one, which leads to travel time derivatives to the power of 4, which we have seen over the years causes complications when trying to solve numerically. Now here, the approach we are taking is to solve it using a neural network. And therefore, we are going to cast this problem into an optimization problem where the loss function will be the residual of the underlying partial differential equation or the underlying anisotropic eikonal equation, which means if we are successful in minimizing the residual, then we can hope that we can get travel times that honor the anisotropic eikonal equation. So this is the idea in brief. Now here I'm going to show you guys how it performs when trying to solve for travel times in BPTTI model. So we had a source here in the center of the model, and what you see in this plot is travel time errors on the left with physics-informed neural networks approach, and on the right is the regular first-order fast sweeping method. As we can see, with pins we can get much better accuracy compared to fast sweeping method. And there are many other advantages of using such an approach. There is no need for label data here. Now, even though we are training a neural network, we don't need label set here because essentially we are using the loss function to guide the training of our neural network. Significant speed up is also possible using transfer learning and surrogate modeling. So compared to conventional methods where there is no transfer of information between solving for one source in a particular velocity model to a different source in a different model, but here we can use transfer learning to carry on that information that we have gained during the training, and for different sources or different velocity model, we can speed up these convergence properties. There's also another important feature, which is easy deployment of computation across a variety of platforms and architecture. So while we have to write separate codes for clusters or GPUs or CPUs for the fast sweeping method, whereas for the pins, we just have our code in, for example, in TensorFlow, and the same code can be ported to different platforms and architectures. Now, this is a mesh-free method, and therefore it's very easy to incorporate topography, whereas if you think of fast sweeping method, you need to use a lot of different variations and complications to incorporate topography accurately. And moreover, one of the main advantage of this approach is that the same approach can be applied to inversion with only minor modifications. So for details, please refer to my upcoming talk at the SEG annual meeting.